Hello, Chem 2 students. This is Mr. Keister here with you again. This is the video for Friday, October 30th, 2020, which is our scheduled 50th day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's look at our do nows and see what our schedule is for today. So today you're going to pick up a new assignment. Page 70 on polarity, intermolecular and intramolecular forces. We won't get through that whole thing today. We're going to do part of it though. Your homework for today was to complete the ionic and covalent bonding assignment. Turn that in. That is due now. Of course, if you're here in school, that should already be on my desk. If you are at home, you need to submit that to me electronically by the time your class period regularly begins. All right, don't be late. You can, of course, check your answers. If you're here in school, they're on the back board. If you're at home, you can check the answer keys page in Canvas. I would hope you would check this one. This one had a lot of stuff on it, a lot of work to show, a lot of drawings that are very specific to the type of bonding involved and the type of Lewis structures that are very specific as to the type of bonding involved as well. So I hope you checked this one. You should check them all, obviously, but there was a lot to show on this one, so hopefully you checked it. So today we're going to continue with Unit 4 and discuss covalent bonding polarity as well as intramolecular and intermolecular forces. So we're going to begin the assignment you picked up today, but you are to do numbers 1 through 6 only. So that's 1, 2, 3, 4, 5, and 6 only. Included in this unit is the memorization of the names and formulas of the 24 polyatomic ions that you have had now for several days. I handed out the list earlier this week, and the first quiz, the first real one, is today. All right, we took a practice quiz yesterday. Hopefully you took the lesson learned there, whether you were ready for today's quiz or not ready at all or somewhere in between, and studied accordingly. So I'm going to throw out the lowest quiz grade. You're going to take 3 quizzes. The first one's today. The next one is Tuesday. We're not going to have one Monday. The next one is Tuesday. And the third one is Wednesday. And I'd like to add to what I told you before. So the lowest quiz gets thrown out. The other 2 get averaged for your final grade. Now, if you get a perfect score today and you get a perfect score on Tuesday, in other words, if you get a perfect score on the first 2, then you are exempt from the third one. You will not have to take the third one, and you'll get 10 bonus points on your quiz score. All right, so keep that in mind. Hopefully you're ready for today's. All right, we'll take that quiz the last 5 minutes of class today. So let's get on to our lesson. So yesterday we talked about covalent bonding, and what I want you to understand is, okay, so remember ionic bonding exists between metals and nonmetals, whereby you have an electronegativity difference between the two of 1.67 or greater, which means then if the electronegativity difference between 2 nonmetals or a nonmetal and hydrogen is less than that, then it's a covalent bond. So keep in mind, though, that although covalent bonds are formed by electron sharing between nonmetals with each other or nonmetals with hydrogen, not all covalent bonds are the same. All right, we've got a big variance there between an electronegativity difference of 0 and an electronegativity difference of 1.66. There's kind of a big disparity there. So unless the electronegativity of the 2 atoms that are sharing electrons is identical or nearly identical, then the electrons are pulled between the nuclei of the 2 atoms as if they were in a tug of war. All right, they're sharing. Think of 2 little kids trying to share a toy. All right, they both grab onto one end and start pulling. All right, if they're not into sharing that much. And so we kind of have a similar situation here with the nuclei of nonmetal atoms. They both want to gain electrons to achieve their octet, but rather than gaining or losing, instead they're going to share. So if we have a difference, a significant difference in the electronegativities, the atom with the greater electronegativity is going to pull the electrons a little closer to it than the other atom is. And then it takes on a slightly negative charge. So we use the Greek letter sigma here. Kind of looks like a musical note with a little minus superscripted to it to show that it's not fully negatively charged, but partially. The other atom, because the shared electrons are pulled a little farther away from it, takes on a slightly positive charge. Again, the Greek letter sigma with a little positive superscript. Thus, a polar covalent bond is a covalent bond whereby the two atoms share the electrons unequally. So now there exists two poles, hence the name polar. One with a slightly negative charge and one with a slightly positive charge. So again, think about that tug of war. So let's say we have an atom over here and an atom over here. This atom over here has a slightly greater electronegativity, and so it pulls a little harder. So think about the tug of war. We have the red flag in the middle, and so the group over here, with the higher electronegativity, is going to pull that red flag. We'll call that the negative charge a little bit closer to it. That's the electrons being shared, of course. Pull a little closer to it, so it takes on that slightly negative charge, and then the other team, since the electrons are farther away from it, takes on a slightly positive charge, although they are still sharing. So in other words, the team with the higher electronegativity doesn't actually pull the electrons completely away. If that was the case, that would be an ionic bond, and then that would be a fully negatively charged ion. And the other one that lost, so to speak, would be a fully charged positive ion. That's not the case here. So again, partially negative and positive, polar covalent bond. In the case where both atoms share the bonding pair of electrons are from the same element, whereby the electronegativity difference is 0, or if they're from two different elements where the electronegativities are very close to the same, then we say that the electrons are shared equally, again, because then the pull from each side is about or nearly or exactly the same. A covalent bond whereby the two atoms share the electrons equally or nearly equally, and thus no poles are established, no partially positive or no partially negative pole is established. We call that a non-polar covalent bond. All right, non-polar. All right, so let's go to the next page. Got a little chart here that describes polarity in terms of electronegativity difference. All right, so you're going to need to know these numbers. All right, they're fairly simple to remember, I think. From 0, if the electronegativity difference between the two atoms is 0 up through 0.49, all right, so basically less than 0.5, all right, that's a nonpolar covalent bond. So of course, two atoms that have identical electronegativity, such as two atoms of hydrogen, their difference would be 0. Of course, that would be a nonpolar covalent bond. But it could be a compound whereby the electronegativities between the two are fairly close. All right, again, difference of less than 0.5. That would also be a nonpolar. All right. If our electronegativity difference is between 0.5 and 1, all right, we say now we're starting to get the establishment of partially positive and partially negative poles. We call that a semipolar covalent bond. So HCl is an example of that. The electronegativity difference between chlorine and hydrogen falls in this range here between 0.5 and 1. With chlorine having the greater electronegativity, then we're showing chlorine with a slightly negative charge next to it, and hydrogen with a slightly positive charge next to it. Again, not fully charged like an ionic compound. If the electronegativity difference is greater than 1, but less than 1.67, then it's polar, all right? So now we have the establishment of significantly more partially positive and negative charge. Water is an example of a polar molecule, a polar covalent bonded molecule. And again, with oxygen being quite a bit more electronegative than hydrogen, the oxygen atom has a partial negative charge next to it, and each hydrogen atom in that molecule of water has a partially positive charge next to it. And then, of course, if you hit 1.67 and beyond, then that separation of charge is complete, all right? And so now we have fully charged positive and negative ions. That's an ionic compound. So, again, less than 0.5 difference, all right? Nonpolar. Between 0.5 and 1, semipolar. And greater than 1, but less than 1.67, polar. And then, of course, 1.67 and beyond would be ionic. And I want you to understand that as you go from electronegativity difference of 0 until you get to 1.67 and beyond, a nonpolar covalent bond is the weakest strength of bond of those four. And ionic is, of course, as we said before, very strong. And so that would be the strongest. So as you go from go from nonpolar to semipolar to polar to ionic, the bond strength is increasing. All right, increasing. In other words, it's going to get harder and harder to pull them apart. All right. So that's polarity. Now, next, nonpolar versus nonpolar or polar bonding versus nonpolar or polar molecules. All right. So let's talk about what we're looking at, the difference there between those two terms. So when a molecule's bonding is nonpolar, and we don't get the establishment of two poles, one partially positive and one partially negative, we call that a dipole, by the way. When a molecule's bonding is nonpolar and there is no dipole form, meaning no partially negative or positive poles, then the molecule itself is always nonpolar. All right, the molecule itself is always nonpolar. So, for example, CH4. All right, so we did CH4 the other day. Remember, it looks like this. The difference in electronegativities between carbon is 2.55 and hydrogen is 2.20. The difference there, electronegativity difference, is 0.35, which is nonpolar. All right. Since the bonding is nonpolar, then there is no establishment of a partial or partially positive or negative pole anywhere in that molecule. So the molecule itself is also nonpolar. So nonpolar bonding yields to a nonpolar molecule. Always. All right. All right. Always. However, now, when a molecule's bonding is polar or semipolar, where we do get the establishment of partially positive and negative poles, and there is a dipole form, which is what we just said, then depending on where the negative charge is located, the molecule itself could be polar or nonpolar. All right? Could be either one. Let's look at an example of each of those situations. So water contains polar covalent bonding, and the water molecule itself is also polar. I want to show you why. All right? So the bonding is polar because the difference in electronegativities between O and H is in between that 1 and 1.66 range. All right. Let's take a look at a water molecule. All right. So we just looked at it a little bit ago. So it looks like so. Remember, oxygen has a slightly negative charge, and each hydrogen has a slightly positive charge. All right. I want you to look and see where the negative charge is. All right. Remember, O is more electronegative than H. All right. So look at where the negative charge is. All the negative charge, again, it's partial, is in the center of the molecule. When that is the case, all right, then we have a polar molecule. All right. In that case, we have a polar molecule when all the negative charge is around the center of the molecule. All right. Now let's look at another example. Here's CCl4, carbon tetrachloride. Contains semipolar covalent bonding. All right. So we're still in a polar. We still have polarity. All right. We still have a dipole form. But now the CCl4 molecule itself is nonpolar. All right. So let's take a look at that. Well, if we look at electronegativities, chlorine is more electronegative than carbon. All right, so remember carbon having 4 open slots is going to be the center of this molecule. So we'll put carbon in the center and the chlorines around the perimeter. All right. Each of these chlorines has 3 unshared pairs of electrons, by the way. I don't want to forget those. Now, chlorine, I'm sorry, C is in the middle, not chlorine. All right, so we have C as the central atom and 4 chlorines around the perimeter. Now, chlorine is more electronegative than carbon. So the partially negative charge is associated with each chlorine molecule or chlorine atom in that molecule. And the slightly positive charge then involving these 4 single covalent bonds is around the carbon. So take a look now and see where the negative charge is now. All right. So the negative charge, again, partial, is distributed, all right, evenly around the perimeter of the molecule. And that leads to a non-polar molecule. All right? So I want you to see the difference, okay? So if we have a non-polar bonding situation, then the molecule itself is always non-polar. But if we have a semipolar or a polar bonding situation where we have the establishment of partially positive, partially negative poles or a dipole, then depending on where the partial negative charge is, our molecule could be polar or it could be nonpolar. Again, if all the negative charge is in the center of the molecule, if the more electronegative atom is in the center, then the molecule itself is polar. But if the negative charge or the partial negative charge is distributed evenly around the perimeter, like it is in CCl4, then even though the bonding is polar, or in this case semipolar, the molecule itself is non-polar. All right? Make sure you understand the difference. Okay? All right, let's go on to the next topic, and we will be then done, or we're close to done for today. Now we want to look at these 2 terms, which sound a whole lot alike, but they are very different. All right? Intramolecular forces. Intra are forces found within a molecule. They are the bonds that holds the molecule together. So nonpolar, semipolar, polar, or ionic bonding. That is an intramolecular force. That's what holds the compound together. All right? Intermolecular forces are forces found between like molecules that attracts them to one another, such as the force that attracts water molecules to each other. All right? What you need to understand is the strength of the intramolecular force that's found within the molecule then determines the strength of the intermolecular forces found between the molecules. All right? So we're going to start with bonding, an intramolecular force. So we're going to look at our electronegativity differences again. Remember, we had it split up in 4 categories. It was less than 0.50, all right, the intramolecular force was nonpolar, covalent bonding. Okay? If it was between 0.5 and 1, excuse me, sorry, that was semipolar covalent bonding. All right? If it was greater than 1, but less than 1.67, it was polar covalent bonding. And if it was greater than or equal then to 1.67, it was ionic bonding. Remember, as we discussed earlier, as you go from a lower to a greater electronegativity difference, the bonding gets stronger. So this is the weakest type of bond. This is the strongest down here. All right? So these are intramolecular forces. All right? Forces found within molecules. This is the bonding. All right? Intra. Bonding. Now, intermolecular force. These are found between like molecules, all right? So the intermolecular force that exists between molecules that are bonded via nonpolar covalent bonding are called dispersion forces. They're also called London dispersion forces. I'll put that in. London dispersion forces. All right. So an example here, so you're going to have, and this pattern of weak to strong is the same here, exactly the same. London dispersion forces are the weakest type of intermolecular force because they exist between molecules that have the weakest type of bonding, all right? This is the strongest down here. So anything that's bonded via nonpolar covalent bonding, so like a molecule of hydrogen or CH4 or NO2, anything where the electronegativity difference within the atoms of the molecule is less than 0.5. All right? Now, with semipolar or polar, all right, we have 2 possibilities of intermolecular force. One is called dipole-dipole forces. Remember, in either semipolar or polar covalent bonding, you have the existence of both partially negative and partially positive poles, or a dipole, all right? Or hydrogen bonding. Hydrogen bonding, all right? I've never liked this term, all right, hydrogen bonding, because if you ask somebody what a hydrogen bond is, there's a common misconception out there. Oh, well, it's found in any molecule that contains hydrogen. No, it's not, all right? And in fact, a hydrogen bond is not a bond at all right? A bond is found within a molecule. A bond is an intramolecular force. Hydrogen bonding is an intermolecular force. It's found between like molecules, all right? It's an intermolecular force. It's not a bond. It's an attractive force between molecules. Hence, I've never really liked that name, hydrogen bond. I think it's a misnomer. I think it's misnamed because it leads people to believe that it's a type of bond found within a molecule, which it absolutely is not. Okay? It is an intermolecular force. Now, it is a stronger intermolecular force than a dipole-dipole force is. All right? This exists. It does involve hydrogen, of course. So this involves compounds that contain hydrogen with only fluorine, oxygen, or nitrogen. All right? If you look at your electronegativity chart, this right here, and you find fluorine, nitrogen, and oxygen, all right? They're right in a row in period 2, all right? Where the in period 2, remember, the nuclear pull for valence electrons, or the Coulombic force, is really strong, all right? And if you look at the electronegativities of those 3 nonmetals, they are among the highest, with fluorine, of course, being the highest, oxygen second highest, electronegativities of all the elements, all right? That is no coincidence, all right? Now, if you look underneath fluorine, you'll see the chlorine also has a really high electronegativity. And there are some texts and some references out there that say chlorine should be included in this group as far as hydrogen bonding. However, most texts and references point to the fact that chlorine, which is in period 3, its Coulombic force, of course, is weaker than it is in period 2. And so that as a result of that, the chlorine atom is quite a bit larger, all right, is quite a bit larger. So the common thought is that chlorine atoms are too big in order to experience hydrogen bonding, so that the H to Cl dipole interactions are weaker as a result of the chlorine being in period 3. So we are going to go with the consensus and say that chlorine is not involved with hydrogen bonding, all right? So when hydrogen is bonded to either fluorine, oxygen, or nitrogen, then the intermolecular force between those like molecules would be classified as hydrogen bonding. So hydrogen with fluorine is HF. Hydrogen with oxygen is, of course, water. And hydrogen with nitrogen is NH3, or ammonia. So only those 3 compounds, exhibit hydrogen bonding as an intermolecular force. Remember, not HCl, because Cl is just too big, which then weakens the intermolecular force. So HCl then would be classified up here with the rest of these, which would be dipole-dipole intermolecular force. So other compounds that are bonded either with polar covalent bonding or semipolar covalent bonding, such as CO2 or SiCl4 or a host of others, would be dipole-dipole. And then the strongest type of intermolecular force, which correlates to the strongest intramolecular force, ionic bonding, actually has the same name, ionic force. So the intermolecular force that exists between compounds or molecules that are formed from ionic bonding, that intermolecular force is called an ionic force, all right? And so any compound that exhibits ionic bonding, such as NaCl, AlF3, and a host of others, would have ionic forces as their intermolecular force. So, again, we start with electronegativity difference, which gives us our type of bonding, which is an intramolecular force. Weakest to strongest, nonpolar to ionic. The corresponding intermolecular force, which is force between like molecules, follows the same pattern from weakest to strongest. London dispersion for nonpolar. Dipole-dipole or hydrogen bonding for both semipolar or polar, and then ionic forces for ionic bonding. Okay, so it all starts with electronegativity. So we have the same pattern of intermolecular force as we do with intramolecular force or bonding. Okay? Make sure you know and commit to memory what we have talked about right here. All right? Very important. So, next page, and then let's finish up. So, general properties of molecular compounds. Well, the reason it says general is because, remember, that the covalent bonding electronegativity difference varies pretty widely. All right, ranges from zero all the way to 1.66, with this being the weakest and 1.66 being strongest. Remember, we go from non-polar, semi-polar to polar. All right. As such, these properties also range fairly widely. All right. So again, as we look at these properties, right, as you go from non-polar to semi-polar to polar, we're going from weakest to strongest bond, and also weakest to strongest intermolecular force. All right. So first, they're formed from the atoms of non-metallic elements with each other or with hydrogen. Of course, that's true of all of these. But now here, generally low, but varying melting points. All right. So a really low melting point would be with the weakest bond. All right. It's not going to take as much energy to melt it if the bond's weaker and the intermolecular force is weaker, of course. So when you go from non-polar to semi-polar to polar, the melting point goes from lower to higher to higher. But even the melting point of a polar covalently bonded molecule is going to be far lower than that of an ionic compound. All right. Generally poor, but varying conductors of electricity. So here again, nonpolar molecules don't conduct electricity at all. Semipolar do somewhat, and polar do much better. Water is polar covalent bonding. We know water conducts electricity quite well, and yet and it involves covalent bonding. But yet other covalently bonded molecules, whereby the bonding is nonpolar and the intermolecular force is London dispersion, which is very weak, don't conduct electricity at all. Okay. Can be gases, liquids, or solids at standard conditions. Well, here again. If the bonding in the intermolecular force is weak, then it's going to take less energy for it to melt and or vaporize, and so those tend to be gases. All right. Oxygen, nitrogen, etc. Nonpolar covalent bonding. All right. London dispersion force as an intermolecular force. They're all gases at room temp. All right. As you then go to liquid and then ultimately to solid, the bonding and the intermolecular force is getting stronger. All right. So again, we have a variation here. And solubility in water varies from low to high. Well, here again, non-polar things don't dissolve in water at all. All right. Semi-polar do better, and polar do very well. So again, we have a wide variance here because the electronegativity difference in covalent bonding varies pretty widely. And so these, we can say that they have generally low melting points. They certainly do as compared to ionic compounds. They are generally poor conductors of electricity, again, in comparison to ionic compounds. Remember, ionic compounds are all solids at room temp, all right, because their bonding is strong and their intermolecular force is strong. On the other hand, we can have any of the three here, and then again with solubility. So we can say that these properties in general describe covalently bonded molecules, molecular compounds, or molecules, but they are going to vary fairly widely because of the differences in the type of covalent bonding, and thus then the type of intermolecular force. So that's where we're going to end today's lesson. Did a lot today. All right. So on your assignment, numbers 1 through 6 only. All right, 1 through 6 only. And that will be due tomorrow. So until next time, this is Mr. Keister signing off. Take care, everyone. Stay safe. Keep working hard and stay focused. Lots more to come. Lots more to come. See you, everyone.